Thank you so much. And first, thanks to the organizers for putting together a wonderful program and for giving me the opportunity to talk today. I will talk about machine learning powered market design, which is based on roughly 8 years of work coming out of my research group. And I will focus on the combinatorial assignment domain, where the goal is efficient assignment of indivisible items M to agents N. And the applications I will study today are spectrum auctions, like what Kevin talked about, as well as course allocation. And in both domains, the agents have complex values for bundles of items, be it a bundle of licenses or a bundle of courses. And this gives rise to value functions that are exponentially sized. And so this is the well-known curse of dimensionality, where the agents can't possibly reason nor report a value for all of these bundles. And the main thesis of my talk today is that a key market design challenge in many domains, but in particular in this domain, is getting the preferences out of the agents and into the mechanism. And the key idea I want to put forward today is that using machine learning can really help to improve preference elicitation by helping the agents focus their attention on the most useful parts of the value space. And in my talk, I'm going to talk about these two different applications. First, iterative combinatorial auctions, where I will give you like 6 different vignettes of a lot of work we did over the last couple of years. And then in the end, I will talk about one specific paper on course allocation that we have done recently. So the starting point for our work on combinatorial auctions is the seminal paper by Oswald, Crampton, and Milgram on the combinatorial clock auction, which is this 2-stage auction design. In the first stage, you have a dynamic clock auction where prices are going up every round until demand is less than supply. And then in the second stage, you have a sealed bid supplementary stage. This is a hugely practical and successful auction design. More than 20 spectrum auctions have been conducted worldwide, generating more than $20 billion in revenue. However, there are also a couple of challenges. One is that the clock stage can take many rounds, and the allocation after the clock stage is often far from efficient. And second, there's a question that the bidders have, which bids to submit in the supplementary round. And there's some experimental evidence by Scheffel et al. And Bichler et al. Showing that the efficiency at the end may often be quite far away from fully efficient. So about 7-8 years ago, together with my former PhD student, Gianluca Brero, and Ben Lubin, who's also in the audience today, we went out to design a completely different kind of auction, which is based on value queries, where the auction mechanism interacts with the bidders via a value query protocol. And we equip the auction mechanism with a machine learning algorithm. And the idea here is that on the micro level, we're using machine learning to learn the bidder's preferences during the running of the auction. And on the macro level, we're using an optimization algorithm to iteratively compute useful queries after every round of the auction. So zooming in a little bit on the key component of this mechanism, we are equipping every individual bidder with their own machine learning model. And the role of that machine learning model is to learn the bidder's preferences. So as an input, the machine learning algorithm gets the previous reports of the agents and learns a value function, VI tilde here. And then we feed all of these learned value functions into a machine learning based winner determination algorithm. We can solve that to optimality, and that gives us an allocation which maximizes social welfare based on these learned value functions. And the key idea here is that this allocation now is a feasible allocation, and we can take the bundles in this allocation and treat them as queries that we feed back to the bidders. And the idea is that these will be very useful queries because they form a feasible allocation that has high predicted social welfare. So this will likely be very useful information to get from the bidders. Now, there's some questions here. One is for the learning part, we need a machine learning algorithm with 2 properties. One is it needs to be good from an economic perspective, being able to predict these highly complex nonlinear values, and it needs to work with a small amount of data because we're learning on a per agent level. Second, it needs to be good from a computational perspective because we need to be able to integrate the machine learning algorithm into the winner determination problem, and it needs to remain computationally feasible. And so one of our main technical contributions back then was that we figured out how to do that with support vector regression with correlated kernels. Now, in terms of incentives, we designed a mechanism back then where the main idea is kind of a textbook idea, where we iteratively called this query module that I just showed you once for the main economy with all the bidders, and then also once for each marginal economy, leaving one bidder out. And this allowed us to, in the end, when we calculate the final allocation and the payments, we're not using any machine learning at the end of the mechanism, but instead, we're just collecting all of the elicited bits throughout the auction to compute the final allocation and the final payments, either VCG payments or core payments. Now, we used a similar approach as what Kevin described in his talk to do computational experiments. Here, we used a simulator that was tuned to the spectrum auction in Canada. And in these results, we found that using our approach, we could beat the combinatorial clock auction by about 2 percentage points in efficiency. Now, one shortcoming of that approach was, or one main limitation, that these value queries going to the bidders required exact answers. So if I asked Pathak, what's your value for a bundle AB, he had to answer $2 million. And that's very costly to figure out for a bundle. And so one improvement we did in a paper we published at EC21 is we developed MLCA with interval bidding, where the bidder could respond with an interval. So for example, you could say, my value is between $1 million and $3 million. This significantly decreases the informational requirements from the bidders. On the technical side, our main contributions there were to combine the machine learning algorithms we had previously developed with a modified revealed preference-based activity rule that made sure that as the rounds progressed, the bounds around the values were being tightened so that over time, the mechanism was eliciting enough information to converge towards the to the efficient allocation. We ran similar simulations as before, and the positive result here is that even though IMLCA is getting much less information than MLCA, it's achieving almost the same efficiency. Now, one shortcoming of the original machine learning-based approach that we used, the support vector regression algorithm, was that it has limited its expressiveness and it was kind of stretching the computational feasibility. So one of my new PhD students who has by now graduated, Jacob Weisteiner, when he joined, he said, why don't we use neural networks? Because they are highly expressive and we can figure out the computational feasibility. So here we now used a fully connected feed-forward neural network. So the idea is on the first layer, you're just encoding the bundles. And then on the last layer, you're just predicting the value of the bundle. And we're using neural networks to learn the value function. And then the key question was, well, how do we formulate the optimization step using these neural networks to still solve the winner determination problem? And this we figured out by using a ReLU activation function in this neural network, allowing us to reformulate the neural network-based winner determination problem into a neural network-based mixed integer linear program, keeping this problem tractable. And here we found that using neural networks instead of support vector regression algorithms, we could further improve the efficiency compared to the prior work. Now, one shortcoming of all of the work I showed you so far is that it was ignoring any kind of prior knowledge about this domain that we are looking at here. Turns out in this combinatorial assignment domain, be it auctions, be it course allocation, two properties usually hold true. One is monotonicity, meaning that an additional item can only weakly improve your value. And second, that the empty bundle has zero value. So the challenge we were facing here is that we wanted to design a new neural network architecture that captures this prior knowledge without limiting the expressiveness. And so this we did by designing a new neural network architecture called monotone value neural networks. And we could prove a universality theorem about this new architecture, showing that any value function that is monotone can be expressed in our architecture. And at the same time, we found that our MVNNs can still be encoded in a succinct way as a min. And then we ran further experiments and we showed that the efficiency can further be improved if we use these monotone value neural networks, which makes sense because they encode the prior knowledge that we have in this domain. Another shortcoming that I haven't told you about so far is that all of the approaches are kind of myopic in the sense that they completely ignore the mechanism's knowledge about the uncertainty about the bidder's preferences. So it's always just looking one step ahead and maximizing in a myopic way. But ideally, the mechanism should think about how uncertain am I about the bidder's preferences in this space of this bundle space or in this part of the bundle space. However, there was no approach that we could use to form a model about this uncertainty that we could then optimize over. So we started out by developing a new approach, and this was challenging because we are in a high dimensional space with very scarce data, and we had to make sure that any model we come up with allows us to, at the end, fit it into a machine learning-based winner determination problem that we can still solve. And so the solution we found here is we developed a specific neural network architecture that actually consists of two connected neural networks, one upper neural network that is responsible for the value prediction, and one lower neural network that is responsible for the uncertainty prediction. And then we designed a special loss function based on 5 Bayesian desiderata that makes sure that the uncertainty prediction satisfies the model uncertainty prediction that we want. This work then allowed us to kind of go the final step and design a Bayesian optimization-based combinatorial auction. So here we could then finally incorporate this model uncertainty into the running of an iterative combinatorial auction. And this we do by designing an upper uncertainty bound based on our previous work of the monotone value neural networks, as well as the model uncertainty neural networks. And then we can optimally control the well-known exploitation trade-off. And this gives rise to a new activation function. So in the optimization step, where we've previously optimized over the neural network representations, we can now optimize over the activation functions that come out of this upper uncertainty bound. And then similar simulations as before show that we can even further improve the efficiency compared to the plain neural network approach and compared to the MBNN approach as before. So the final point I want to make about the combinatorial auction workstream here is some ongoing research we're doing at the moment. And here we're kind of going back to demand queries, because obviously value queries are not the only way to do this, but we want to leverage the power of prices. And the idea that we're currently exploring is designing a CCA, but where we are enhancing the clock phase of the CCA with a machine learning based approach. The idea here is to train each bidder's machine learning based model based on their demand query answer, so which are tuples of the form bundle and price at which this bundle was optimal. And then in every round, we're going to find an approximate clearing price vector P star that minimize this function W, which is the sum over the indirect utility functions of the bidder and the indirect revenue function. And this is an idea that was previously put forward by Brera et al. And here we see in this chart that with our approach, we can, after very few rounds in a domain called LSVM, we can achieve efficiency around 96% after roughly 20 rounds, while the CCA is at that point still around 88%, and later it plateaus around 91%. So this is just after the clock phase without the supplementary round. So this is the end of the combinatorial auction work stream. And now I want to tell you about one paper called the course allocation paper. And here I have to thank the organizers of NBER, because roughly 5 years ago, when I presented the first version of the paper in the previous work stream, after the presentation, Eric approached me and said, hey, can't we apply the same ideas that you just showed about the auctions to the course allocation problem? And then, only 5 years later, we have another paper. Yes. So in case you're not familiar with the course allocation problem, the problem is we want to assign university courses to students. We have a limited number of seats, and no monetary transfers are allowed in this domain, in contrast to the previous domain. The dimensions of interest here are efficiency, fairness, and good incentives. And our goal is to design a practical mechanism that is good in all 3 dimensions. So the state of the art is the course match mechanism designed by Eric. It's a practical implementation of his approximate competitive equilibrium from equal incomes mechanism that he put forward in his 2011 paper. And the course match mechanism makes a good trade-off between efficiency, fairness, and incentives, compromising a little bit on all three dimensions, but achieving a good trade-off that works in practice. And this mechanism, course match, has been adopted in many top business schools, including at Wharton and at Columbia. Here's a quick overview of the reporting language that a course match uses. First, the students, for every course that they're interested in, they can report a base value. So for example, I can enter a value of 50 for the first course, a value of 100 for the second course. And second, for some courses, I can additionally report an adjustment. For example, for two courses, I can say I have a -1 or a +50 value for the pair of the two courses if I get both of them. And then the utility of a schedule at the end is simply computed as the sum of all the base values of courses contained in the schedule plus any adjustments if the student reported any pairwise adjustments. Now, Budish and Kessler did a very nice lab experiment before course match was deployed in practice. And while on average, the students really benefited from this new mechanism compared to the previously used BPA mechanism, they also identified several shortcomings. One is that the students showed significant cognitive limitations. They only made use in a very limited way of this very nice reporting language, reporting only a few base values on average, and most importantly, only reporting one adjustment on average, and actually the median number of adjustments was 0. You might also be concerned about the limited expressiveness of the language. The language by design can only capture at most quadratic preferences, and we don't know if that's enough for all students or not. But I think most importantly, they showed that the students made significant reporting mistakes, ex post showing them alternative bundles they could have gotten, and the students reported that they would have preferred another schedule. And this significantly harmed the efficiency of the mechanism. So this is the motivation for our work, using machine learning to kind of fix these reporting mistakes, leading to better efficiency. And here, so one way to understand our mechanism is to contrast it with the course match mechanism. And the course match mechanism essentially just has two phases. In the first phase, all the students enter their reports into the graphical user interface, and then you run the course match mechanism, which has 3 stages, and then the final allocation is computed. So what our mechanism does is it essentially inserts itself into the middle between the first and last phase, which gives rise to this iterative machine learning-based preference elicitation phase. And the idea is similar to the auction-based work, that we're going to maintain a separate machine learning model for every student. The input to the machine learning model is a course schedule, and the output is going to be the predicted utility for that schedule. And then at the end, we're going to run the original course match mechanism, but instead of the GUI preferences, we're going to use the trained machine learning models as the input. And so in phase 2 of the mechanism, we're going to first create an initial data set to have an initial machine learning model based on the GUI reports. Then in phase 3, we're going to compute an ACEI based on these initial machine learning models. And then the interesting thing happens in phase 4. This is the iterative preference elicitation phase. We're going to ask every student a pairwise comparison query. And after answering one query, we're going to immediately retrain the machine learning model and repeat. And this takes, in practice, less than 2 seconds. So this can be done in real time. And the student can answer 0 or as many of these pairwise comparison queries as they want. And this can be done completely asynchronously between the students. And we use these very simple pairwise comparison queries where the student just looks at 2 schedules and then says, I like this one better than this one. There's no need to enter any values or any adjustment numbers or anything else. So to evaluate this, evaluate the 2 mechanisms, we designed a new simulator using a similar approach as what Kevin described. We paid particular attention how to model the students' reporting mistakes. And we allow students to forget a base value, forget an adjustment, make mistakes when reporting a base value, or make mistakes when reporting an adjustment. And then we fitted the simulator based on the real data that Budish and Kessler reported in their 2022 paper. And here's some of the empirical results from the simulation. So on the x-axis, you see the number of comparison queries that the students answered, 1, 5, 10, 15, 20. And on the y-axis, you see efficiency here measured as average student utility. And in yellow, I'm showing the efficiency achieved by course match. Of course, it doesn't increase with the number of comparison queries because there are none in course match. And in blue, we see our mechanism. And with 10 comparison queries, we can increase efficiency by 7%, and with 20 by more than 11%. And this increase is even larger if we look at minimum student utility. So these are the worst students in the population. So here it goes up by more than 15 or by more than 24%. Now, the last point I want to make is in the spirit of what Typhoon presented yesterday in terms of minimally invasive market design. Throughout this whole project, we designed the mechanism to be as easy as possible to deploy in practice if a university wanted to do that. So first, MLCM as designed is plug and play compatible with the existing implementation, because you can just use the existing GUI, then use this new process in between, and then at the end feed it, if you want to, into the course match algorithm. Second, it allows for asynchronous interaction between the students. There's no synchronous interaction needed as in an auction. Third, the participation is completely optional for the students. You can completely opt out if you don't like machine learning. And fourth, opting into the machine learning component is beneficial even for a single student. So even if nobody else does it, you benefit from it yourself, because it will help you elicit your preferences better and capturing it better. And this is shown here in this table. If you're the only one who participates and nobody else does, then you will prefer the outcome under MLCM in 72% of the cases. You would prefer the outcome under course match in 6% of the cases. And on average, your utility would be increased by 11%. Okay. Let me conclude. So the key challenge that I've put forward here is to get the agent's preferences out of their head and into the mechanism. And the main idea I wanted to put forward is to support the agents via an ML-based iterative preference elicitation mechanism. There are many things to consider. Sufficiently expressive machine learning algorithms, for example, neural networks, making sure it's computationally feasible. Often that means being able to encode it as a mixed integer linear program. Incorporating prior knowledge if you have it in your domain, modeling uncertainty if that's important, and then making sure you have a simple user interface. In the course allocation domain, for us, that meant using pairwise comparison queries, and of course, aligning the incentives of the agents. Thank you very much.